Okay, we're gonna review the one of Basil J. Hiley's papers on consciousness. This is the title of the paper. Can quantum mechanics solve the hard problem of consciousness? And when we look at the paper, it says, but what if Newton's first law is not valid at the quantum level? Because in Brownian motion, they are not equal. The backward and forward derivatives. And so what you end up getting in quantum physics is that you have because they're not equal, that means they're noncommutative in time. And therefore we have the commutator and anticommutator, which is the Moyel bracket and the Jordan or the Baker bracket as the Jordan product. So when you have the plus, that is the anticommutator of the forward and backwards derivative, and then the minus is the Moyel bracket. And the difference between these two becomes the nonlocal quantum potential. So then what they're saying is, what Basil J. Hiley is saying is that the noncommutativity then is a necessity because these don't vanish. And this is due to the Planck's constant is part of the imaginary number phase space. So basically that would be your noncommutative frequency. So we scroll down and basically what they're saying is that you get the quantum potential energy, as I just said, and that's ends up being the average as the Jordan bracket, the Jordan product becomes the quantum trajectory, the Bohmian trajectory. So he's saying that you derive this from Moyal algebra, and so then he's saying that the classical physics is an approximation of the non-commutative formalism. And then he's saying that at first, when you just use it in the Bohmian physics, in the Schrodinger equation, then it's easy to ignore it. That's what the physicists have been ignoring it, because it just goes to the classical limit, and so you get the same result as the Schrodinger equation. But he's saying here that when you use the spin and relativistic equations, then it's necessary to have that noncommutativity. It doesn't go away. And that but the irony is that this is not discussed in the context of the non-commutative Bohmian physics, because it's wrongly believed that the Bohmian physics isn't possible, cannot be applied in the relativistic domain. So it's this logical catch-22. It's like, well, we can ignore it, but then it doesn't work in relativity, so we can ignore it again. But that's not true in both cases. So here one cannot simply split the wave function into real and imaginary parts. One has to use the noncommutative algebra, indicating the essential need for noncommutative techniques. And this is the same relativistic quantum approach that Alain Kahn is using. by relying on the Dirac spinner. Okay, so he goes into that math, and then he goes down and says that that this phase space, in spite of the uncertainty principle, uses the noncommutativity, and it turns out that when you take the exponential of the classical Poisson bracket in the Moy algebra, then what you're doing is you're lifting the symplectic geometry. You're using the covering group of the symmetry. And it says this is similar to what Feynman was doing for the sum over pass approach. But the problem with Feynman is he was using the renormalization to cover up the noncommutativity. So what Basil J. Hiley is saying that if you just use the first order differential equations, you can overlook this significance of the Poisson bracket, that when in the exponential form it's non-commutative, and it can't be reduced. So, and this is the equivalent of the Baker bracket as the anticommutator, the Jordan product. And so the expression it uses 3 points, and because it's 3 points in phase space, it's inherently non-local. And then it has to contain that non-locality. And it says that the secret of classical mechanics itself has this non-locality that was so far missed simply by using Newton's or Hamilton's differential equations in motion. So in other words, you have to use this Moy algebra to see the secret of the exponentiation of the Poisson bracket. The symplectic geometry preserves the phase areas, and the difference lies in these phase areas in quantum mechanics. And so in classical physics, you can assume the area can be shrunk to a point of the, which would be the geometric continuum as a symmetric rest frame. In quantum mechanics, it can only be shrunk to a phase area cell based on the Planck's constant reduced Planck's constant right here, h bar. And this is why you have the uncertainty principle. And so what happens is that normally the h bar is reduced to 0. And then they say, if you read the other links I gave yesterday, they say, well, then we don't have to deal with the murkiness of the anticommutator. We can ignore the murkiness of the Jordan product and the Baker bracket. And then, but in the quantum structure, if you make h bar to 0, then the whole structure literally blows up because it's an infinity, because you're dividing by 0. And so in the physical world, h bar is not 0, and it follows that classical physics cannot hold in the very small. And so this is what Feynman tried to cover up with the renormalization tactic, but that covers up the noncommutativity. And then we get to the really interesting part, because he says this idea is very significant for biological phenomena. Already there is mounting evidence for quantum effects occurring in biological systems. And then he says, we feel it is essential to draw the reader's attention to this rapidly developing field, which has been held back in the belief that, quote, wave decoherence is the fatal factor that destroys quantum effects in living systems. This negative outlook traps us into a totally obscure notion of, quote, wave-particle duality and all the